beginning of the third week, so we're sort of at the end of chapter 1, beginning of chapter 2, as far as placement in the text. So what I want to talk about today is, I want to give you what the definition of an observable is in quantum mechanics, but let's recall from our SG experiments. Let's recall a few facts from our SG experiments. So, if we had an SG Z apparatus, we had Z plus and Z minus states where the observable is the spin angular momentum of the electron. And we said that Z plus has spin plus H bar over 2, and Z minus has spin minus H bar over 2, where H was the H is Planck's constant. And that's 6.62 times 10 to the minus 34 joule seconds, so tiny. And H bar is equal to Planck's constant divided by 2 pi. So these are the physical observables. And we call the, what we want to do is call this operator, there's an operator that goes along with an observable. So for every physical observable, there is the corresponding operator. So for an SG, for an SGZ apparatus, we call the operator SZ hat, and for an SGX apparatus, we call the operator SX hat, and similarly for in the Y direction, SY hat. Okay, and the hat denotes an operator. Okay, so now I'm going to write down in short notation here. I can write down SZ hat, and I can write Z plus minus for the ket. I don't want to have to write down a whole, I can, so that plus minus goes with this plus minus h bar over 2 z plus minus. This just means, this is shorthand for sz z plus is equal to plus h bar over 2z plus, and sz z minus is equal to minus h bar over 2z minus. Okay, just so we can fit, so we don't have to do too much writing. So we also have Sx hat on, if I'm operating on the x kets, x plus and minus, this is equal to plus minus h bar over 2 x plus minus, oops, and sy hat and y plus minus. Okay. So far, these are abstract operators. So we have not defined representations of the operators, and I'll explain what those are in just a moment. Okay, so, but what we want to do is just make sure that we keep in mind that these are, if we make measurements with an SGX, SGY, or SGZ apparatus on these kets, these are the results that we should get. Okay. Are there any questions so far, just over the basic definitions? Okay, so our electron, okay, that's a general state for an electron in terms of its spin. So there are only two basis states. And these are the states, or these states are the results, the possible results of a measurement. Okay, remember when we make the, when we do make the measurement, whatever the electron is in some state here, but it's going to pop into one or the other states. We will only get one, it will come out as a plus electron, a state in Z plus or a state in Z minus. Okay. So for a general system now, so this is, not a two-state system. The state ket is the state ket of a particle is some linear combination of basis states of an observable that you could measure. Okay, so let's suppose that we have just an arbitrary observable, and let's call it A. Which is an operator. And let's suppose that the base states are given by a collection, so we can call it A1, A2, up to AN. Okay, so this means that there are capital N possible outcomes of a measurement. Then if A is the observable corresponding to these states, we will find the following, that if I make a measurement on, say, the state A1, so this just looks exactly like this equation here. You know, I'm making a measurement on the state ket Z plus with this operator SZ, and I'm going to get this this value out. That means I'll have some value here. Let's call it lambda 1. This is, and I'll get my same state ket back, just like we did here. If I put in my state ket, a particular basis ket, then I get the same basis ket back with some number in front of it, and that's called its eigenvalue. Okay, so if I were to do the same thing with the second basis state, I would get something like lambda 2, A2, and so on. So in general, I would have A operating on A sub n, some ket is lambda n A sub n, where this is called an eigenvalue. And the AN is called an eigenket.
Is this a similar concept to the eigenvalues and eigenvectors we learned about in linear algebra? I think we had to calculate them in the first homework.
Same thing, yeah. Okay, so this is a very special equation. It's called an eigenvalue equation. And just like you learned in linear algebra, if I take an operator like a matrix, I operate it on a vector. If I get back the same vector with just some number in front, then that's called an eigenvalue equation, and the number that you get out is the eigenvalue. Okay, so if we have, so let's just suppose then that we have a general state then. So a general state, we would write psi, and now I'll have C1, A1, plus C2, A2, plus up to Cn, A1. Okay, and I'll just, instead of writing it all out, I will probably in the future just write the sum over I equals 1 to n Ci A sub I. Okay, so that means that if you have, so, you know, if this, I could have some giant machinery now. This is my, you know, my A operator. I can send my send my particle in, and then out here, we will find the different kets. All coming out, and so the measurement will select one of these eigenkets. Okay. So now let's go ahead and write if this is the way we write the ket, let's go ahead and write the corresponding bra. So the bra vector is going to be C1 star A1 plus C2 star A2 and so on. Okay. And we want to demand also that if I just have a particle coming in with some state psi, if I don't do anything, then we remember that we demanded the last time we wrote this down that we should have a normalized ket vector. That means the particle has to be in some state. And what does that mean? Well, if we write this out, so I'll have, let's do this in a general fashion. So the bra vector we can write is the sum over J, and then Cj star Aj in general. I'm just rewriting this expression in terms of, this is one, the sum goes from 1 up to n. And now if I do the inner product, then we have the following. Just write down exactly what these two things are. So we've got one sum J equals 1. I've got this object, and then I've got the sum over I, Ci, Ai. Sum goes from 1 to n. Okay, so this is just a little notation. And now, what we would like to do, you can see that I'm going to have a bra here with an A in it, and it's going to hit a ket here with an A in it. So we will have the inner products AJ, A sub I for I equal to I and J up to N. Okay, so we've got a whole bunch of inner products here. Okay, now is where you can think of these things as just ordinary vectors. Right, we're just, this is the inner product between them. It tells you how much overlap is between the vectors. So if we have an orthonormal set, then we can write AJ, A sub I is equal to delta Ji. I defined the Kronecker delta, right, already? Okay, so that means that A1 is equal to 1, and then A1 with AK is equal to 0 for K not equal to 1. That just means all the other ones are 0, and so on. So A2 will be 1, but A2 for any other is 0 for K not equal to 2, okay? So they're just, the only time that I'm gonna get a 1 is when J equals I here. Okay, so that, when we're always going to work with normalized orthonormal vectors, because it's the, you know, it just makes calculations easier. So we can always, you can always find an orthonormal set of vectors using the Gram-Schmidt process that you've learned in linear algebra, but typically we'll just be given that. Okay, so if this condition holds, then we can rewrite psi. We can rewrite this equation. So let's call this equation 1. So if we rewrite 1, we have that this is equal to, now I can bring out all my sums. And then I'll have C J star, C I, and then I'll have AJ, A sub I. Okay? And now this is just the delta. This is the Kronecker delta, delta Ji, which means that it's 0 unless J equals I. Okay? So what does that mean? It means I will collapse one of these sums. Because, for example, if J equals 1, the only contribution I'll get is when I equals 1. Otherwise, this would be 0. So I'll collapse one of the, you can pick whichever one you like, collapse this I equals 1 sum, and then let this I equal a J. So this would be equal to then the sum over J equals 1 to N, and then we have Cj star Cj. Okay? But this is what? This is just the sum J equals 1 to N over the magnitude of Cj squared. So we have the sum J equals 1 up to N of Cj magnitude squared is equal to 1. The coefficients, this is a constraint on the coefficients. And this is normalization. any questions so far?
So what was that last word there? This is a constraint on the what?
Constraint on the coefficients?
Oh, okay.
Coax.
Coef.
Sorry.
Okay, and while I'm here, recall that the magnitude of Cj, any particular Cj squared, is, this is the probability that a measurement would yield, or would find the particle in state J, AJ. Remember that from before? Okay, so what this sum is just the sum of the probabilities. And the sum of the probabilities must always be 1. So this is just, you've seen this, whatever the probabilities are for an event, all possible outcomes, they must sum to 1. Okay, any questions so far? All right, so let's talk now about expectation values. So if we have an observable A, and we have a particle in some state psi, the expectation value of that observable is given by this bracket. And it's always, whenever you take an expectation value, you always take it with respect to a particular state. So this is equal to taking A in between the ket de Bras like that to squeeze it. Okay, so these are identical. Okay, another way to think about this is, if when we were talking about amplitudes for processes, you can think of this as in the following way. I start off in the state psi. A is an operator that does something to psi. If if it's a vector, you can think of it being rotated or something like that. And then I take the inner product with psi after A operates on it. And that tells you how much overlap there is between the vector A operating on psi and psi itself. Okay, well, I'll talk about that more later, but I'm just mentioning it now. But that's what the expectation value is. Okay, and so let's go ahead and calculate this and just see what we get. For our general state psi. So if we let psi be the state, so it's just this generic state where it's some combination of coefficients and the basis over the basis vectors. Then let's calculate what this is. Okay, so we have, let's just write it out again. So psi A psi will be, and I'm just going to use the stuff we've written down over there. So we've got the sum over J, and we had CJ star AJ. So that's that psi. And then we've got our operator A, and then the sum over I 1 to n CI AI. Okay? Now, A is an operator, and I can move, this is just a sum, so I'm just going to let A come in and operate on the ket. Okay, it's just going to come in and operate on A1, A2, and so on. So we'll use the fact that A on A sub I is going to be given by lambda I A sub I, right? This is just our eigenvalue equation. So that means then that the expectation value of A will be the sum over J and I from 1 to n. We'll have Cj star. Now A is going to hit this A sub I and give me a lambda sub I. So I'll have a lambda sub I, and then I'll have AJ A sub I. Okay? And again, this here is just this Kronecker delta J sub I, so it's going to kill this one sum, and then I have to either turn my J into I's or my I's into a J. So let's do it, we did last time, we'll just turn the I into a J. So this will be the sum over J equals 1 up to n. This will be Cj star Cj. So I'll again have the magnitude of Cj squared times lambda J. And this will be the expectation value of A. Okay, so what is this? What is this? If I have if these are the eigenvalues for, when A operates on A sub I, okay, these are the values that you get. This is like the h bar over 2 minus h bar over 2 in the spin experiment. Okay, but now these could be, different things. And remember now that these Cj squareds, they're summing to one, and these are the probabilities that a measurement would find the system in any particular state. So if I take probabilities, this is the probability of finding state J times the eigenvalue of state J, then what am I getting, what is the expectation value giving me?
Well, the magnitudes, because they're summed over the entire thing, would be 1, right?
Yeah.
And then that would be times the sum of all of the eigenvalues, right? And then sum all the eigenvalues too? Or it only have the one eigenvalue?
No, I mean, I've got each eigenvalue here. Each eigenvalue is being weighted by this probability factor.
Yeah.
So what happens when I sum up a given set of things given a probability factor? What am I calculating?
The weighted average?
Right, it's
Yeah.
an average. Exactly, it's an average. Okay, so that's what the expectation value gives you. It gives you a weighted average. Okay, so now we're going to be calculating these things, but remember that so the expectation value for any particular observable is very different from the measurement, right? The measurement only gives you one of the. If I take an actual measurement, I only get one of the states, so it means I only get one of the eigenvalues. Okay, so the expectation value here is the average. It's that weighted average over the states, and it depends on the particular coefficients in this you plug in that were part of the state. Okay, so now that we're talking about probabilities and averages, we can define variance here. So let's define the uncertainty or the variance as we'll define it as delta A, and that will be the square root of A squared inside minus outside. Okay, so the variance here, remember, for a distribution gives you like the width of the distribution. So if it's like a bell curve or a Gaussian distribution, that that will give you the width. Okay, so we'll calculate this. This is the uncertainty. So for measurements, this would be these would be in some state psi. When we talk about the uncertainty in the position and the momentum of the particle and try to discuss Heisenberg uncertainty principle, this is the uncertainty that you would calculate for a particular electron. We can calculate later on, not now, but we will be able to calculate things like the uncertainty in the position of a particle and that kind of thing. Okay, so now let's calculate, we're going to have to calculate this A squared on the inside. So what's that? So just based on what we did over here, what do you think the answer is? It means we have an A squared here.
Yeah.
So what does that give me?
squared.
It's just lambda squared.
Oh,
Hmm.
I like
So this will be sum over j equals one up to n of cj squared lambda j squared. Okay, so we're gonna use these relationships here. Okay, any questions before we do some examples? So we'll go back to our electron spin system here. So we'll be back in two-dimensional Hilbert space, so it makes it easy. Okay, so let's do the first example. So let's suppose that our state ket is just the z plus, we're in the z plus state. And let's calculate delta SZ, the uncertainty in SZ. Okay, so first we have to calculate SZ, the average, and this is in state psi, that's just going to be Z plus SZ Z plus. What's this? What is SZ when it operates on Z plus? What do we get?
Oh,
Is it
Z,
C1? Z plus?
square the magnitude times an eigenvalue?
Remember, just think physically. Just forget about the left-hand side, forget about this, the broad vector.
Oh, is it
What is SZ
h
on-
bar over 2? A positive h bar over 2?
Right, it's h bar over 2. That will come out, it's just a constant, and then I'll have Z plus, which gives me what?
Z1?
Is
Z1.
Z plus is in the direction of Z plus, right? So, yeah, so this is just plus h bar over 2. Everybody see that? Okay, so now we have to square it, so SZ with the square on the outside, that's just h bar squared over 4. And then we have to calculate SZ squared. So what is SZ squared operating on Z plus?
Square square of 4.
Why is that?
Because you square h bar over 2.
Right, you're just operating twice, so first time you operate, you pull out an h bar over 2, second time you operate, you pull out an h bar over 2. That make sense? Right, this is just h bar over 2, Z plus, SZ, Z plus, and then h bar squared over 4, Z plus, Z plus. Right, so this is h bar, this is equal to h bar squared over 4, so then delta SZ, it's the square root of the difference of these two.
Which
but
is 0. So
it's
the
the-
variance is 0.
Right.
I got lost in the calculations, that wasn't obvious.
Okay. Okay, so notice that if the state was, in a particular eigenstate of the system, right? It's not in a linear combination, it's in an eigenstate. If it's in an eigenstate, then if I have a measurement that's gonna give me one of the eigenstates, its uncertainty is going to be 0, because it's in an eigenstate, it's not in a superposition. Okay, let's do a little more complicated one here. Let's do, now let's suppose that psi is in an eigenstate. Okay, and then calculate delta SZ. Okay, so now we have to calculate psi SZ psi. That's going to be, when I flip this around, I'm gonna get a factor of 1 over the square root of 2 from the two sides, so I'll get a half. And then we'll have z plus plus z minus. Then we'll have sz, the operator, operating on z plus plus z minus. Okay? So let's let sz now run through here. So I'll have the same thing here. Now when sz goes through here, what am I gonna get in front of this z plus?
Plus h bar over 2.
Right. So I'll have h bar over 2 z plus. Then what am I gonna have in front of z minus?
Minus
H
h bar over 2.
Minus h bar, right?
I'm getting that.
Okay. So now I can bring out these h bar over 2's, but what, I'll have an overall factor here of what, h bar over 4. And then what am I going to have?
Let's just FOIL, so you get z plus z plus plus z minus, so you get 1 plus 1, so you get 2.
Well, I have, remember I've got a minus sign there.
Well, that's,
Yeah, so makes it a difference of,
so it's 1 minus, oh, it's 1 minus 1, so it's gonna be 0.
Right, so this will be 0. Okay. Does everybody want to see that in greater detail, or?
no.
I think you got it.
Okay, so then let's do psi sz squared. Psi. So we'll have 1/2 z plus plus z minus. And now we'll have an sz squared here, so what am I gonna have in parentheses here?
H bar squared over 4.
And what's the second term?
H bar squared over 4, because it gets multiplied twice. Like 2 negatives to the point of that.
Right, everybody see that? So there's another plus h bar squared over 4 z minus. So now what do we have? We've got h bar squared over 8. And now what do I have in multiplying this h bar squared over 8?
2.
Right, 2. Okay, so then delta sz is equal to the square root of, now let's see, this is the inside one, so it's h bar squared over 4 minus 0, so this is h bar over 2.
erase that. I already erased it.
No,
No, it's
you need to take a picture. Yeah, if you want, yeah.
Yeah, alright,
Did you get it?
good.
Okay, so let's calculate, let's do another example. Calculate delta SY for the state, psi equals over root 2 z plus z minus. Okay, so now we have an interesting issue here. We're gonna have to answer this kind of a question, right? What is SY on Z plus? Well, what do I do?
Well, this would be like putting like the Z plus particles through the Stern-Gerlach Y, right? It'd be like one of the experiments you showed us the other day.
Yeah.
I just don't know how to explain that in the math. Because it would split it 50-50 into Y plus and Y minus. That's my guess.
Well, what did we do what did we derive last time in the notes?
I'm not sure if you have to change it to basis, so why?
Yeah, change basis, right?
We have to change the basis, yeah.
That's what it is.
So remember that, Z plus was one over root 2 of Y plus Y minus. And Z minus was an overall I over root 2. An overall minus I over root 2 of Y plus minus Y minus. Okay, so we can calculate these things now. So SY on Z plus is 1 over the square root of 2 of SY on Y plus. What's that? What is SY? So I'm doing a Stern-Gerlach measurement on my Y plus.
I'm assuming it's H bar over 2.
Yeah.
Right, it's plus H bar over 2. Y plus, and then
Minus H bar.
minus H bar over 2 Y minus. So this is then H bar over 2 roots of 2. Let's see. Y plus minus Y minus. Okay. And then S sub Y on Z minus will be I over root 2, and then we'll have, minus I. And then H bar over 2 Y plus. And now I'm gonna have a minus from hitting the Y minus, but I've got the minus sign here, so this would be a plus H bar over 2 Y minus. Okay, so now that you know how SY acts on both Z plus and Z minus, we can calculate everything that we need to. Okay, so let's, what time do we have?
Yeah,
It's
15
46.
minutes.
20 minutes.
4:30 already? Wow. Time flies. Okay. All right, let's see, let's go ahead and finish this calculation. So this is minus I h bar over 2 roots of 2. Y plus y minus. Okay. Now, if you wanted to be really clever, you'll notice that this thing looks like z plus, because I've got the plus here, and I can just write z plus directly from this. And then up here, if I stick an I in the top and the bottom, then I can write z minus. Okay, so you know, let's go ahead and do that then. And this should simplify things then. So we'll have sy z plus is equal to, let's see, that's this thing. So I need to stick, if I have a minus I, let's go ahead and write h bar over 2. I can put a minus I here and a minus I down below, and then a 1 over root 2 y plus minus y minus. So this part, minus I over root 2 y plus minus y minus, that's z minus. So I can write this as I h bar over 2 z minus. And then we can write sy plus on z minus, just directly from here is minus I h bar over 2 z plus. Okay. So the expectation value in, if we have our state kit, in psi, well, I'll have a factor of a half coming from the bra and the ket that I make out of psi, and then I'll have z plus z minus sy hat z plus z minus. Now we can use the two things that we've just discovered. So this will be 1/2 z plus z minus, and then here we have on z plus we get I h bar over 2 z minus, and then when sy acts on z minus, we'll get minus I h bar over 2 z plus. Okay, so then we will have, this will give me a, this z plus and this z plus will give me a 1. So I'll have minus I h bar over 2 from there, and then here I'll have a plus I h bar over 2. So, I'm sorry?
I just said, it gives you 0, is what I said.
Okay, so a lot of work to get 0, but that's the way it goes. Okay, so now we, if you if we let S operate twice, then, you know, something that, we're gonna change the signs a little bit, so let's just see what happens here. So sy squared on z plus will be what? So let's take let's look at this form right here. If I let S act again, Sy, then I'll I'll have a plus h bar over 2 here, and I'll get another minus here, so this will make a plus. So I'll have 1 over the square root of 2, h bar squared over 4, y plus, and then I'll have a plus h bar squared over 4, y minus. Okay, and what is that in terms of z? This is, I'll have y plus plus y minus, that's just z plus again. So this is just h bar squared over 4, then I've got the 1 over root 2, this is just z plus. And then sy squared on z minus, let's see, I'll have a minus I. Here I'll have another h bar squared over 2, and then this one will become a minus. So I'll have h bar squared over 4, y plus minus h bar squared over 4, y minus. But this is h bar squared over 4, and then I'll have a minus I with a y plus minus y minus. So we'll just have z minus again. So then sy squared psi will be 1/2, we'll have z plus z minus, and then we will have h bar squared over 4 z plus h bar squared over 4 z minus. And then this will give us h bar squared over 8 times 2, which is h bar squared over 4. Okay, so then we'll have the delta sy in the state psi is just h bar over 2 in this particular state. Okay, is everybody comfortable with that?
I think so.
All right. Okay, so now, there are faster ways to do the calculation, and that's where we come to doing representations of operators in terms of matrices. So the key point to remember when we're doing all of this, you have to make sure that you understand what basis you're in. Otherwise, you'll lose control of the calculation. So let's now represent the ket vectors and the operators in terms of matrices. Okay, so we get to choose what we want the basis to be, so let's make a choice that's easy. So I mentioned this before, we can go ahead and write our our kets in this form. And so the bra vectors, remember, I have to turn them sideways So that's 1, 0, and the broad vector for z minus is 0, 1. So that the matrix multiplication works when I take the inner product. So z plus is the inner product written in terms of matrices is like this. So this gives me, you know, I go across and down. So this is just 1, and then z plus with z minus would then be 1, 0, 0, 1, so I would just get nothing. Okay, does everybody see the matrix multiplications there? Okay. All right, so that's easy. We just pick the basis states like that. So once we make this choice, then that will fix the, you know, when we calculate the matrix representations for these other operators, they're fixed by our choice of the kets that we choose. So we're choosing a basis. And so whatever we choose is going to come back in the form of these operators. So what is the matrix representation of SZ hat? Well, this depends on the basis. So let's first choose the Z basis. Okay, and then we will write SZ hat. We can put a little superscript here that tells us what basis we're in. Okay? Just to be clear. And so let's go ahead and write it down. We can write the matrix now just as A, B, C, and D. So we don't know what they are, we have to find them. So we'll use the fact that we know that SZ on Z plus is equal to plus H bar over 2Z plus, and SZ on Z minus is minus H bar over 2Z minus. Okay, that's the data that we have to tell us what these coefficients are. So now we just go ahead and multiply through. We'll use these vector representations here for the kets. So first, let's write down A, B, C, D, and we'll let it operate on 1, 0. Now, what do we have to get? We have to get plus H bar over 2, 1, 0. That's just a statement of this equation. Okay, so now we can do the multiplication. So if I do the top row, I get A times 1 plus B times 0 is equal to H bar over 2. So we have that A plus B times 0 is equal to H bar over 2. Okay, so that's just 0. And then here on the bottom row, we have C equals 0. Okay, so from this top equation, we get A is H bar over 2 and C is 0. Okay? Now we multiplied B by 0, so we don't know anything about B. It doesn't have to be 0. But let's see. So now we can, and the same thing with D, we multiplied it by 0 here, so we don't know what D is. So let's use the other equation. So now we have AB, CD operating on 0, 1, and this has to give us minus H bar over 2 times 0, 1. And so the top row will give us B equals 0. and then the bottom row, I'll have D equals minus H bar over two. Okay, so we've solved all of them, so we have now that SZ is equal to, in the Z basis, H bar over two times the matrix 1, 0, 0, minus 1. Okay, all right, well, so that's the representation of SZ in this particular Z basis. So now if you want to calculate some of these things like the expectation value, so what is, let's, let me do it over here, there's more space. Actually, what time do we have? Is it?
4:42.
Let's go ahead and stop here. I think that's a lot, and then we'll